All right, so in this lesson, we're going to look at our algebra procedure and apply our algebra skills to finding the inverse of an exponential function. This prior knowledge reminds us that the inverse of any relation being the word we use to describe any set of ordered pairs in whatever form it may take, that inverse is a switching of x and y coordinates for each point. And so our negative 2, 7 in the inverse becomes 7, negative 2, 5, 0 becomes 0, 5, 3, negative 8 becomes negative 8, 3, and 7, 4 becomes 4, 7. When we're working with functions, because we don't have individual x and y values, a key part of the procedure for finding the inverse is to switch the variables of x and y. So that's one of the things that we're going to be looking at is changing our variables. Another thing that I just want to remind you of is that we'll use our inverse notation, which uses a superscript with the function name. So if f is our function, then this becomes the notation for the inverse of f of x. One of the things that too, we won't be doing this today, but it is something that is in this lesson and in the notes that I want to remind you about, is that the graphs of inverse functions or inverse relations are reflections of each other over the line y equals x, which is shown as the dashed line in these graphs. So if we folded the graph along the dashed line, the function and its inverse would match and meet each other. Since we're working with exponential functions, what I want to point out again is that the inverse of an exponential is a logarithm function. And so if we're starting with an exponential and finding its inverse, we should end up with a logarithm function. And whatever the base is of our exponential function should then also be the base of our logarithm function. And so that's part of kind of the visual to make sure at least some of what we would be expected to do actually happens within our math. All right, so here is the procedure for finding the inverse of an exponential function written out. So we'll most often have function notation like f of x, g of x, h of x, and so on. So we want to change that function notation just to a y variable for this process. And then using the definition of an inverse, we are going to interchange or switch the two variables. So x will become y and y will become x. Reminder not to move any of the numbers or other symbols in the function. So everything else stays exactly where it is. Then we begin using our algebra skills to solve for the y variable. And so this is one of the procedures that we can use, is we can isolate the power expression. So if there's anything which would be the base and its exponent, so like b to the power of a, we get that part by itself. So if there's anything added to this or subtracted from it or times it or it's being divided by something else, we're going to undo all of that using our reverse order of operations. And once we have this power isolated, we'll have exponential form. And then that will allow us to go to the second step here, which is to write what we now our exponential form into its logarithm form. And then we can continue solving for the y variable if that is necessary. Sometimes it won't be necessary and sometimes it will. It depends on the original structure of the function, the exponential function. And then to finish it up, we'll change that y variable to the proper inverse notation. All right, so this process works for exponential functions of any base. We will look primarily at our most common bases. I know base e and base 10 will be in here. There might be a base 2 thrown in also. Those are usually the most common base values in calculus problems, so that's why we focus on those. But like I said, the procedure works for an exponential function of any real number base. All right, so we will begin. First step is to take our function notation and look at it as a y variable. Second step is to apply the definition of inverse, which says that all of the x's and y's switch. So all the x's are represented by the variable of x, all the y's that correspond are represented by the variable y. So y becomes x, and x becomes y. Now we get into the algebraic portion where we have to solve for y. Now in this one, remember the part A is to isolate the power. The power is the base with its exponent. E is the base, and its exponent is y plus 3. So that's already isolated. So that step A, we don't have to do anything extra. We actually have the structure for that step A in this part. Now, the next part is to take, this is exponential form. We have to see this is exponential form. And now we're going to rewrite this in its logarithmic form. And I tend to like to start with my exponent. So we know that our logarithm is equal to our exponent. Our exponent is the y plus 3. So we know that's what our logarithm is going to be equal to. Over here I have my logarithm symbol, log. And then I have its subscript base. The base of the logarithm is the base of the power, which is e. And then whatever remains, which in this case is x, that is my argument, which I'm going to put in parentheses. I don't have to if it's a product or a single variable like this, but if it does involve addition or subtraction, then I do have to put it in parentheses. So it's a good habit to have. So now what do I do? Well, that third step is to continue solving for y as necessary, which here it is because we have to undo the plus 3. But another thing we want to recognize about this is that log base e is our natural logarithm. So this becomes our ln symbol. So we now have the natural logarithm of x equals y plus 3. And we're going to subtract the 3. And this is another thing that helps by putting the parentheses around the x. Our i's won't connect the x and the minus 3. So the minus 3 is going to go after the argument that's in parentheses. So now what I have is the natural log of x followed by that minus 3 is equal to the y variable. And then my last step, I will change my y to the appropriate inverse notation. My original function was f. So that y becomes f inverse. And notice that I'm starting with that. Functions always start with the function name, which here is f inverse, equals the natural logarithm of x minus 3 to finish it up. All right, so here we have another problem to talk about. The big difference is with, just recognizing, given the structure of the original exponential function, making sure that our algebra procedure is valid. The first two steps always will basically be the same. So we'll take our function notation, which here is g of x, and change it to what it represents, which is our y variable. The structure here is telling us we have 2 times a base of 10 to the exponent of x minus 5. So you might want to add that times, but it's not absolutely necessary as long as you understand they are separate from one another. So remember that in the second step, what I want to do is switch my x and my y. So y becomes x, and x becomes y. Oops, want that to be a 5 still. And now I begin the process of solving for y. And in solving for y, I want to isolate the power in that part A. And so the power again is the base with its exponent. The base here is the 10. The exponent is the y minus 5. So we have to undo the times 2, dividing both sides by 2. So now we have x divided by 2 equals 10 to the power of y minus 5. At this point, those parentheses are pretty much optional, but I'm keeping them. So now remember, once we have that power isolated, this is what we refer to as exponential form. Therefore, our next step, once we have created our exponential form, power equals a value, then we change it to the logarithm form. And the logarithmic form, logarithms are always equal to the exponent, which is the y minus 5. Over here I have my log symbol, and then the subscript, which is my base of the power, which is 10. So I have log base 10. And then after that is my argument, which is whatever I have not used yet, which is the x divided by 2. So again, the parentheses here are technically optional because I don't have any addition or subtraction in my argument, but it's good to visually separate so you understand what is your argument's in parentheses, and later on what isn't part of your argument, and keep it out of the parentheses. So now we're going to move into the step, or the third step, which is the C that says to continue solving for y. And similar to the previous problem where we had a log base e that we needed to also recognize was our natural logarithm and change the symbol, here we have a log base 10, which is what we refer to as the common logarithm. And when we have a common logarithm, we don't include the subscript base. We just simplify that to log followed by the argument, and we know that it means there's a base of 10. And then we would also undo the subtraction of the 5, adding 5 to both sides. And the 5, remember the argument was fixed earlier on, so that can't change. So x divided by 2 was and will remain the argument. So the plus 5 goes after and outside the parentheses. And that then is going to give us the log of x divided by 2 followed by the plus 5 equals y. And our inverse notation becomes, remember our original function was named g of x, so now we have to use g inverse. So g inverse of x equals the log of x divided by 2 followed by plus 5, like so. All right, so here we're at a new function, k of x, also exponential, base e in our power. Let's begin with our procedure. So we understand that k of x is our y variable. We understand that anytime when we're taking a function of this type and finding its inverse, that we use the definition of the inverse to change the variables, but nothing else moves. So x becomes y becomes x, but everything else remains as is. Then we begin the process of solving for y. Remember that first step is to isolate the power. The power again is the base to the exponent. Here our base is e and its exponent is 3y. So to isolate it, we have to undo the addition of 5 that follows it. So we would start by subtracting the 5 from both sides. So now we have x minus 5 equals e to the power of 3y. So once we've isolated that power, so in this step A, isolating the power always creates the exponential form. And once you have exponential form, your next step will be to rewrite it in its logarithmic form. So logarithms, remember, are equal to the exponent value. Here our exponent is 3y. And then over here we have our log symbol followed by our base as a subscript, which is e. And then whatever we have not used is the argument. So that's the x minus 5. This time the parentheses are required because of the subtraction. If you do not have parentheses, like if you wrote log base e of x minus 5, people who understand math look at that and say x is your argument, and only x. So in order to make your argument the x minus 5, it must be in parentheses. So that is crucial. So now what I'm looking at is, as I move into step C here, my log base e again is my natural logarithm, so that becomes my ln followed by my argument of x minus 5. And to isolate or solve for y, I'm going to need to undo the multiplication with the 3. So I have to divide by 3. So here I want to show you, remember that when we have functions, we would not actually see this notation for our function. All right. So what we would actually see is that as we simplify this and do this division by 3, it's actually going to be written as multiplication of the reciprocal of 3. So there's a 1 times this natural logarithm, because we can say 1 times anything anytime we need to. And that 1 over 3 becomes a factor in front. And so that's actually when we look at graphing logarithm functions, that's our a value. So this is saying we have 1/3 times the natural logarithm of x minus 5, our argument. So that's how you should be writing that, okay? Recognizing dividing the whole thing by 3 isn't really what we want to recognize this as. We want to recognize this more as a times 1/3. And if you prefer, instead of doing division by 3, you can, of course, do times 1/3 on both sides, because multiplying by the reciprocal of a number is the same thing as dividing by it. So now we've got our inverse notation. So this function, as I recall, was k. Yep, so k of x. So my correct inverse notation is k inverse. So k inverse of x equals 1/3 times the natural logarithm of the argument x minus 5, like so. All right, in this example, which will be our final example for this lesson, we're looking at a base 2 exponential function. So here the procedure does not change. So again, the first thing is to recognize our function notation here of p of x is of course our y variable. This structure means 7 times the base of 2 to its exponent of 5x plus 8, followed by the minus 3. And our second step in finding an inverse is to switch our variables. So y becomes x, and x becomes y. So now we begin the part of the problem where we solve for y, which is where most of our work, of course, occurs. So that first step, that step A, is to isolate the power. Again, the power is the base with its exponent. So our base here we have to see is the 2, and its exponent of the 5y plus 8. So that means we have to undo the multiplication with the 7 and the subtraction with the 3, and we have to use that reverse order of operations to do this correctly. So reversing the order of operations tells us that we would begin by undoing subtraction. So we would add 3 to both sides as our first step. So now we have x plus 3 equals 7 times 2 to the power of 5y plus 8. Now we will undo the multiplication by dividing both sides by 7. And this time you can write this as division by 7 or times 1/7, your choice, because this is actually going to become part of the argument. So there's no simplifying to do because there's no common factors within x, 3, and 7 to reduce. So I would probably just leave this as x plus 3 over 7, or maybe as 1/7 times in parentheses x plus 3. And it, like I said, whichever you prefer is fine with me. I don't care. If we were going to graph it, I would say the second one would be preferred, the 1/7. All right, so now what I've got is my power isolated. So now that I've isolated the power, that is my exponential form. So from there, my next step, part B, is the logarithmic form. So logarithms are always equal to the exponent, which is the 5y plus 8. Over here, I'll use my log symbol followed by the subscript base. The base of the log is the same as the base of the power, which is 2. And then after that is my argument, which is the part that I haven't used yet, which is my x plus 3 divided by 7, or my 1/7 times x plus 3. And so I can write it like this. Or if you prefer, you can also use that. All right, so now we move into part C. And in part C, we continue solving for y. And this time, we have a log base 2, and that is its only symbolic notation. So only our common logarithm and our natural logarithm have anything else, have any other type of notation that we have to simplify. So log base 2 will remain log base 2. So I'm going to, again, use my reverse order of operations, and I'm going to subtract my 8, because I have to undo addition before I undo multiplication with that reverse order of operations. Remember, my argument is already fixed. That's why I put it in parentheses. So this goes after those parentheses. So now I have log base 2 of my argument followed by minus 8 equals 5y. And now I'm going to undo my multiplication. And here's where, again, I don't want that all divided by 5 because, well, that just doesn't look like how we see functions. So what I'm going to do here is use that other strategy. So instead of dividing by 5, I'll multiply by its reciprocal. So I'll multiply by 1/5 on both sides. And any number times its reciprocal is 1. So this times this is 1. 1 times y, of course, gives me y. And this is my 1/5 times my log base 2 of the argument x plus 3 divided by 7 followed by minus 8. So now all that remains is to change my y to its inverse notation, which, given I think our function was p, yes, it will be p inverse. So we have p inverse of x equals 1/5 times the log base 2 of x plus 3 divided by 7 followed by minus 8. So that's probably as complicated as they get with all of the undoing algebra, with, having addition, subtraction to undo a couple times, having multiplication to undo a couple of times to create the inverse function in whatever base logarithm it is. All right, so that does finish up this lesson.